Why don't we see relativistic effects in our daily lives? And the answer to that question lies with gamma. And so here's the Lorentz factor, 1 over the square root of 1 minus v squared over c squared. So I want to make a little table down here where we use different v's, we put in different speeds, and we see what gamma is. And the first one that I'm going to put in is 3,000 meters per second. Okay. Now, just so you know, 3,000 meters per second this is the same as 0.00001 C. Okay, so that's 0.001% of the speed of light. So, what is gamma at 3,000 meters per second? And also, by the way, 3,000 meters per second is about 6,700 miles per hour. So we're talking pretty fast. Okay, so if I do this, and I square it, I go 1 minus that, and I take the square root, my calculator says gamma is 1. Now, it's not actually 1, but the point is it's so barely off of 1, my calculator can't display the difference. So this is about 1. And that right there tells you everything you need to know. Why don't we see relativistic effects? Because no matter, as we're moving around in our daily lives, gamma is essentially 1. The Lorentz factor is essentially 1 for all of us. So in all of our formulas, for example, time dilation, delta t equals gamma, delta t naught. What happens? Gamma is essentially 1, and so this says that delta t equals delta t naught. Oh, okay, we're all in the same frame there. We're all going to see the same elapsed time between any two events. If we're talking about length contraction, okay, then it's gamma L naught. Excuse me, I did that wrong. Gamma L equals L naught, but gamma is 1. So guess what? This just says L is L naught. So we all see the same lengths for everything. Everything is the same as its rest length. We don't see length contraction. If we talk about momentum, well, guess what? This is just going to become the classical form that we all know and love. P equals mv. If we're talking about kinetic energy, now this one, it's not obvious. You put in 1, you'd be tempted to say that it's going to become 0. But I made a video showing, and it's down in the energy section of this homework, but I made a video that shows that when gamma goes to 1, this reduces down to the classical form 1/2 mv squared. That's not at all obvious. That's why I made a video that goes through and shows this. But the point is, in our daily lives, our speeds are so small compared to the speed of light that the Lorentz factor is essentially 1, and no matter what interactions we're having, and so we don't see any relativistic effects. Let's look at some higher values for V. Let's say 10% of the speed of light, so 0.1 c. 0.1 c. Okay, so if I do that, that's going to be 1 minus 0.1 squared, take the square root, and I get 1.005. So at 0.1 c, gamma is 1.005. So still not much of a difference, but this is significant enough that generally we consider 10% of the speed of light to be roughly when you really need to you need to take into account relativistic effects. And it always depends how precise you're trying to be. You might need to take into account relativistic effects sooner, depending on how precise you're trying to be. But continuing on, so that's
1.005. Let's just jump up to, say, 0.5 c. Okay, so if I do that, take the root and then reciprocal. Let's do that properly. 1.157. So you can see, I mean, here we are, half the speed of light. That's pretty fast. That's 1.5 times 10 to the 8th meters per second. I mean, that's ridiculously fast. And yet gamma is only 1.1547. Still not very big. Let's jump to let's say 0.8 c. Why not? So we'll do that. And it's squared, 1 minus 1.7 0.667. So we can see we haven't even hit 2 yet for gamma. And I'm going to do just a couple more. Let's do 0.9c. So I'm going to do just a couple more. Boo! That was a little bit more than I wanted. So if we do that, we get 2. Oh.
2.294. Okay, I'm actually going to stop there. That's plenty. We can see how it's going. But this is the whole point. We don't see relativistic effects because we're moving too slow. You have to be moving pretty fast before you do see relativistic effects. There is one place where relativity does matter, and that's with GPS. It's the first practical application of relativity. Prior to GPS, there really was no practical need for relativity. But if you don't take into account relativity, then GPS doesn't work.